So we've been talking about the physical transformation of vaporization or evaporation, where we're going to have some particles of our liquid have enough kinetic energy that they can actually then escape the intermolecular forces between all the molecules in the liquid state and become part of the gas state. So, thinking about that, we said that as we increase the temperature of that sample, we increase the average kinetic energy of the particles, which means more of the particles in the solution or the molecules will have enough kinetic energy to escape the liquid phase. And as we increase temperature, we see that vapor pressure increase. That vapor pressure is the number of particles that are in the gas phase compared to the liquid phase. So as the temperature increases, that vapor pressure increases until we hit a point where the vapor pressure is the same as the atmospheric pressure. So that atmospheric pressure is the pressure of the gas just in the air around you right now. If you're close to sea level, it's about 1 atmosphere. It's probably like 0.998 something right here in Seattle. Now, if you're higher up, that atmospheric pressure decreases, right? It'll be lower if you're at a higher altitude. So once that vapor pressure has increased to the point where it's the same as the pressure around the liquid, then we have boiling occur. And so what happens is then the interior molecules of our sample, rather than just the surface molecules, will have enough kinetic energy to become a gas. Typically, below that atmospheric pressure for the vapor pressure, it's just the surface molecules that are at the higher, have enough energy to escape into the gas phase. They also have less intermolecular forces to break to be able to do that. So at that boiling point, gas will form in the interior of the liquid. And that's the bubbles that you see form when you see boiling take place. And then they like float up to the top and they pop out. So when you see those bubbles inside the liquid, that's our liquid molecules converting into the gas phase, clumping together, and then leaving the liquid. So as we input heat energy into our liquid sample, the temperature of the sample increases and increases and increases and increases until we hit a point where the vapor pressure has become the same as the atmospheric pressure and we have boiling occur. Now, at that point, all of the heat that we put into or energy that we put into the sample is going to go to converting molecules from the liquid phase to the gas phase rather than just heat the temperature or heat or increase the temperature of the sample. And so what we see in these what we call phase diagrams is that we have the temperature increasing as we add heat in our liquid phase until we hit that boiling point, that temperature with which the liquid's going to boil. And then we see that the temperature doesn't change. It'll stay the exact same temperature until all of the liquid is converted into a gas. And then it'll become a gas. And then it'll start increasing in temperature again as we add more and more energy into the system. So, one big clue that you're in a phase transition like boiling or melting or freezing or evaporation, or I guess instead of boiling, evaporation, is that it's that the temperature remains constant through the whole process. Now, if you think about this from the perspective of cooking something like cooking pasta, right? You're going to want to cook that food at a consistent temperature through the whole process. And so that's why using boiling water, not just is it hot, but also it's going to be at the same temperature the entire time. And so you'll get a nice consistent amount of heat applied to the food or transferred into the food that you're trying to cook. And so let's think about what's happening then at each of these different phases of this phase diagram. Now, hopefully, from 161, you remember that we were looking at how heat flows in and out of a system, and we were able to calculate the amount of heat that was going into a system with temperature change. So that's this equation right here. That heat is that Q is equal to the mass times the specific heat, which has units of joules per grams degrees Celsius or grams Kelvin. And then our change in temperature, which is our final temperature minus our initial temperature. And so we would see for any amount of a change in temperature, it would correspond to a amount of heat being absorbed by the sample. And so we can calculate that amount of heat that's flowing into the system as it's heated for this part of the diagram where temperature is changing. However, when we don't have a temperature change, if that delta T is zero, then using our Q equation for heat would mean we would just calculate zero, that no heat was being applied because there wasn't a temperature change. So we can't use the same method to understand how much energy will it take to boil liquid. We can't do it the same way as figuring out how much energy will it take to heat a sample of water from 50 degrees Celsius to 75 degrees Celsius when it's not boiling. And so instead, what we do is we actually use that enthalpy of vaporization that we talked about. So that's going to say the amount of energy that's required to vaporize an amount of the substance that you're looking at. Typically, we have kilojoules per mole or joules per mole for our units. We'll be looking at, okay, how many moles do we have of this sample? All right. Well, we know that the amount of heat that's required to actually evaporate 1 mole is this. So we could then figure out what it would be for our sample of a specific amount of moles.